Hello guys, welcome back to TechDose, and in this video we will see the open addressing in hashmap. So the prerequisite for watching this video is my previous video on chaining in hashmap. You should watch this video and then come back to watch this open addressing. So I hope you have seen this chaining video. So let us now proceed with the explanation of open addressing. Well, open addressing is also known as closed hashing. In this case, the number of elements which are present in the map should always be less than equals to the map size, because the elements are stored in map and not in the form of a linked list as we were doing in case of chaining, right? So let me just show you by an example. Let's say this is our map. Our map is having size 4, right? So the keys are from, let's say, 0 to 3. Now we are inserting 4 elements. So first what we will do, we will fetch the element to the hash function, and it is calculating the value which is the key value. So 10 will be inserted at key 0. So 10 is inserted here. Similarly, 11 inserted at 1, 12 inserted at 2, and 13 inserted at 3. So the entire map is full here, right? Now you cannot insert h of, let's say, something like 20, which will be giving, let's say, key equals to 0, because there will be a collision, right? And now this entire map is full. So even if you move to some other slots, all the slots are filled. So this is one of the limitation in case of open addressing, that once the size has been fixed, then you cannot insert more elements. More elements can only be inserted if you dynamically allocate more memory into the open addressing table, right? Now, as I already explained in the previous video, load factor was nothing but alpha equals to n by m, where n was the number of elements in the table and m was the number of slots in the table. Now in case of open addressing, the number of elements in the table should be less than equals to the number of slots in the table. Therefore, this numerator will always be less than equals to the denominator, and that is why this alpha value will range from 0 to 1. I hope you understood this load factor as well. Now let us see how do we handle collision in case of open addressing. Now in case of collision, we will make minor modifications to the hash function input and recalculate the hash value again. So let me just explain you by using an example. In this case, let us say that we will be using the same example, right? So h of 10, 0. So the format is like h is the hash function, k is your element, that is input element, and I will be the collision number. Now initially we are calculating for value 10 and we have not found any collision for it. Therefore the collision value will be 0. And after applying the hash function on this, you are getting key value 0. We just assume this, okay? So this 0 will be checked, and at 0 this 10 is inserted, right? Similarly, we will do for this 20. 20 is given as input and the collision number is 0 because we have not found any collision for 20 right now. We will be fetching this 20, 0 to hash function. Key value is 1. So we will go to 1 and insert this 20. Similarly for 30, 30 is inserted at 2. Now let's assume that you also want to insert 40. So far we have not seen any collision. So collision value is 0. Let's say the key value which it is giving as output is 0. So we will be going to key 0. This is key 0, and we will check if this place is empty. So this place is not empty, it is occupied, and that is why there is a collision. So we will do minor modifications to the hash function input. Now let's say that minor modification is incrementing the collision number, right? We are using the same hash function. We are giving 40, 1 as input. So 1 is the collision number since we have seen one collision. Now let's say the output key is 2. Now we will go to key 2. At key 2, 30 is present. So it is already occupied, right? So again there is a collision. So we have encountered collision 2 times. So again we will use the same hash function. We will give collision number as 2, and this is our input number 40. And now when we calculate the hash, it is coming as 1. So we will be going to 1 and we will see that it is already occupied by value 20. So again we cannot insert this 40 at position 1. Again we will repeat the same process, incrementing the collision number, right? And let's say this time we get the key value as 3. So at position 3, this 40 will get inserted because this is empty, right? So we were successfully able to insert this 40 at position 3. Okay. Now what is the worst case time complexity of insertion in this case? So as you have seen, 10 was inserted in just 1 time, 20 was inserted in just O1 time, 30 was also inserted in O1 time. But what happens if you find collisions? So in case of collisions, the maximum number of times you will have to probe, that means you will have to check for slots, will be equals to the table size. So let's assume that the table size is n, then the number of slots you need to search is basically n, okay, because n minus 1 other slots may be full, and that is why the insertion time will be order of n. Now once we have seen the insertion part, if the table size is n, then the hash function should make sure that if you are doing n number of recalculations, then you should be able to check all the n keys, okay. So in this case I have mentioned that if m is the number of slots in the table, then on m recalculations we must probe or check all the m slots, right? Because let's assume that you just probed this like 40,0 value is 0, 40,1 value is 2, 40,2 value is 1. Now let's say on 40,3 the value was not 3 but it was again 0. And again for 40,4 the value was, let's say, 2, and so on. So you are just falling in a cycle of 0 to 1, and again after 1 you are going back to 0, again to 1. So if you are not using a proper hash function, then you might be missing out on some of the slots, you might not be using them, okay. So you should make sure that you are using such a hash function so that if your size of the hash is equals to m, that is the table size is m, then on m times recalculations you should probe, that is you should be able to check all the m keys, right? So this time complexity is written in such a way that your table size is n, okay. So if your table size is n, insertion time will be order of n. Now what about searching? Like the way you have inserted, let's say you want to search for this 40, okay. So what will you do? First you will be calculating its key, so it will be h of 40,0 and its value will come out to be 0. So you will go to index 0. So this index 0 is containing value 10, it is not 40. So since you have seen an occupied cell, you will continue, okay. So you will calculate the hash value again, it will be h of 40,1 and its hash value will come out to be 2. You go to this 2 and you see that value is 30, it's not 40. It is occupied. So it means that there is a possibility that the element might be present in this probing chain, okay. Now since you have seen 2 times collision, the third will be h of 40,2 and this time the output will be 1. So you go to index 1, this is also occupied but the value is not equal. That is why we will keep probing. So h of 40,3, right? So the value in this case will be 3. You go to index 3 and you will find that it is having 40. So we have found it. So searching is also taking order of n time. And deletion will also take order of n time, because in order to delete an element you need to search it. And searching is taking order of n, okay. So I hope you understood how the collision resolution is done in case of open addressing. Now there is a special case of deletion which I will be showing you right now. Now how to handle deletions in case of open addressing. Let's assume that we are taking the same example and the same sequence. So first is h of 10,0. So it is the 0th collision number, 10 is the element. Key is 0, so 10 will be inserted here since it is empty. Similarly 20 will be inserted at key 1, 30 will be inserted at key 2. Okay. Now you have the next element as 40. So this 40 is giving us key 0 on collision number 0. But 0 is already occupied by 10. Okay, so we will keep probing for the next spot. Now this h of 40,1 is giving 2. So 2 is also occupied. We will keep probing for the next collision number 2. It is giving value 1. So 1 is also occupied. We will keep probing. So collision number is increased. Now 40,3 is giving output as 3. We will go to 3. It is unoccupied. So we will keep 40 here, right? Now let's say we want to delete 20. So we will go, like we will calculate the hash of h of 20,0. It will come out 1. We will go to 1. Yeah, 20 is present here. So we will just remove it. Okay. So now this slot 1 is empty. This is just a blank slot right now. Okay. Now let's say we want to search for 40. Then how do we do it? Again, what we will do is we will do h of 40,0 since collision number is 0. So what will be the output? Key will be 0. we will go to 0, it is occupied and the value is 10 here, right? So we will keep probing. Now since we have seen one time collision, its value will be increased, collision number, and h of 40,1 was giving key 2, so we will go to 2. Okay, 2 is also occupied, we will again increment the collision number like it is a second collision. Now the output will be this one, key 1, right? So we will go to this key 1 and 1 is empty. Okay, so this one is empty because it was already deleted. Now once we find a cell as empty, we will have to end our search. Okay, so this I have already mentioned on the previous slide. We will keep recalculating unless all the M slots are probed. If all the M slots are probed and you haven't found any unoccupied space, that means that your entire hash map is full and you cannot insert any more elements, right? Otherwise, the second case is we won't stop unless we find a free slot. Okay, as soon as we find a free slot, we will stop there. Now in this case, we have found a free slot. Okay, so while insertion, if the elements were to be inserted using this same collision sequence, then if there was a free slot, then 40 would have been inserted here, right? So since there is no 40 and this is also empty, then we can think that 40 might not be present in this entire map. Okay, but that is not the case. Actually, the sequence was like key 0, then key 2, then key 1, and then key 3. Key 3 was containing value 40, right? But suddenly this one become empty. This become empty. So now while probing, we go to 0, it is occupied. We go to 2, it is occupied. We go to 1 and it is empty. So we are stopping here and we are not searching further. Okay. So that is why this is creating a problem. Now you might think that, okay, don't stop here and keep searching. Now in such a case, let's say your key was actually not present in the map. Then you will end up searching all the n elements. So the search time will always be order of n if the element is not present in the map. So that doesn't make any sense. We are using map because we want to decrease the search time. Okay, that was the entire goal of using it. So we cannot just keep on searching randomly. We cannot just keep on searching even if we find the empty slots. So what do we do in this case? Now one way to avoid this situation is, once we delete an element, we can use a marker. We can use a marker to handle the deletion case. So what we can do, we can just mark it with some value. Let's say we mark it by value d, saying that this slot is empty right now, but there was some element present here, right? So in this case, once you start searching, start from 0, you go to 0, it is 10, you go to 2, it is 30, you go to 1 and it is marked as D. This means that this slot is empty, but there was an element already present here. So that element might have been 40 or this element might have been any other element, right? So in this situation, you will continue your search once you see this marker D. Okay. So you will continue your search and you will increase the collision number. So it will be h of 40, 3. And now the slot number given is 3. You go to 3 and you will find that 40 is present here. So you have found your element in this case. So if you want to do deletion in case of open addressing, then actually you need to use a marker, right? In order for the search pattern to know that it has to continue the search, it won't stop on seeing this empty slot. So I hope you understood how to handle the deletion case in case of open addressing. Now let's talk about the advantages and disadvantages. So the advantage of using open addressing is there is no wastage of memory like we saw in case of chaining. Okay. And the disadvantage is that the number of keys for the hash table, that is the hash table size, has to be known. Otherwise, we may require dynamic memory allocation. And if we are allocating memory dynamically at some random time, then we may not get contiguous memory assignment. And for random access, contiguous memory is very helpful. The second thing which I found was open addressing is much more complex to implement as compared to chaining. Because in chaining, you don't have to worry about anything. You just calculate the hash function on your key once and you get a key. So this will be element. Okay, this is not key. You give the element as input to the hash function, you get a key. Now based on the key, you go to that map slot for that key and then you will search for the element on the linked list which is being pointed by that slot. So this is like extremely simple to implement. If you are asked to implement hash map, then you should always choose chaining, because open addressing will be difficult with the markers as well, right? So this was all about open addressing. Okay, in the next video I might compare open addressing with chaining. I hope this video was helpful. If you have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.